Okay, so let's do a recap from yesterday. And what we discussed was the current status of neutrino physics, in particular neutrino parameters. So we saw that we have two mass square differences which have been measured, one around 7.5 10 to the minus 5 eV squared, and another one around 2.5 10 to the minus 3 eV squared. And we said that this implies that there are three massive neutrinos, at least, which can be ordered, whose masses can be ordered in two ways. The normal ordering, where you have M1 smaller than M2 smaller than M3, and the inverted ordering, where you have M3 smaller than M1 smaller than M2, yeah. Okay, and then three mixing angles. As a 3 by 3 unitary matrix is parameterized indeed by three angles. Theta 1, 3, which is around 9 degrees. Theta 2, 3, which is possibly even maximal, so okay. And theta 1, 2, which is around 33 degrees. And we said that there start being hints for CP violation in the lepton sector, although it's too early to know for certain. So what we are going to do today is to address the open questions which remain. So first of all, the nature of neutrinos, and I already discussed several times why I think this is really a crucial question in this area of research. Then the values, the absolute values of neutrino masses, because so far we only know mass square differences, but we don't know the overall scale, and we don't know the ordering. So the absolute value of neutrino masses. And then I will discuss leptonic CP violation. There's furthermore the discussion of testing the three neutrino paradigm, but this is something we are not going to cover today. Three neutrino mixing. And as several people came to ask me about sterile neutrinos, etc., is something that I'm going to mention, discuss a little bit briefly in the last lecture, on lecture number 5. Okay, so let's start with the first question, the nature of neutrinos. I already mentioned this, but this for me really is central in neutrino physics, and the reason is that the nature of neutrinos is directly related to the symmetries, in particular lepton number, conservation or not. If you have a Majorana neutrino, you cannot distinguish the neutrino from the antineutrino, and this can only happen if lepton number is not a conserved symmetry of nature. Therefore, when you extend the standard model to understand the origin of neutrino masses, then you will either extend it in a lepton number conserving manner or not. And most of the models we have for neutrino masses lead to Majorana neutrinos and require lepton number violation. The typical example is the CISO that I'm going to discuss tomorrow in the first lecture, in lecture 4. So formally, we can define a Majorana neutrino, a Majorana field. Has this been discussed in any other lecture? No, so, but you know what a Majorana field is? Yes, so it's a field which is equal to its conjugate. Do you know what's the conjugate formally? Okay, not everybody, so I'll do a little aside in which I define the charge conjugate of a field. So let's look at charge conjugation. So I define the charge conjugate psi C to be C, where this is a matrix, psi bar transpose. This matrix C has the following properties. When I apply C gamma alpha transpose C dagger, this gives me minus gamma alpha. And furthermore, C dagger is the identity, and the C transpose is minus C. And for instance, in the Weil representation, C is I gamma 2 gamma 0. So, and this operation changes the quantum numbers to its opposite. So, so what we'll discuss later, it's very important to remember that if I do the C conjugation of a left-handed field, I will obtain a right-handed field. We can see that in the Weil representation. If I take the C of psi left, this will be I gamma 2 psi left star, because the psi bar transpose contains a gamma 0 that I'm cancelling with that gamma 0 there. And so this is I 0 sigma 2 minus sigma 2 0 applied to psi and to 0, and here I define this psi left in terms of an eta component, eta star. And as you see, this will swap the two, the up and down components, and so will give me I sigma 2 eta star 0, which is a right-handed field. What I would like you to do as an exercise, because it's just a kind of useful exercise to do, but it's really a very important property to remember, is to demonstrate that the C of a left-handed field is right-handed, but not using a specific representation, but just the properties of the C matrix. So now we can go back to the Majorana fields. So, and this is the formal definition. Let's look at their properties. So first of all, a Majorana field satisfies the Dirac equation. So, as you know, well, I can write it down. I gamma mu d mu minus m psi equals 0. Now we can write it in terms of its chiral components, and if I do that, the Majorana field needs to be written in terms of a left-handed component and a right-handed component, which is simply the conjugate of psi left, using this property here, that psi left C is a right-handed field. And you see immediately that that satisfies the Majorana condition. And this also tells you immediately that you have only 2 degrees of freedom and not 4 like a fermionic field. Because if you want, 2 degrees of freedom are here, and this contains the other 2 degrees of freedom, but which are identical to these ones. So you reduce, the Majorana condition reduces the degrees of freedom to only 2. And in fact, specifically, you cannot really talk about neutrinos and antineutrinos for when you talk about a Majorana field. You can see that also when we look at the quantization of the field. So I can write down the Majorana field in terms of only one type of operator. So I will have 1 over 2 pi cubed, the square root of 2e, and then my integral in d3p. And now I have only, I sum over the helicities, and I have only the operator A. B corresponds to A, so I will write A h of P, U h of P, e to the minus I P x, plus A h dagger of P, V h of P, e to the I P dot x. Normally, for a Dirac field, this would be a separate operator, a B dagger. But if I apply the Majorana condition, this tells me that B needs to be equal to A, and I end up kind of confirming what I've just seen before, that I have only 2 degrees of freedom. And the last property I want to mention is that Majorana fields don't carry any quantum number. In particular, they don't carry lepton number or let alone any charge. So if I do a U1 lepton transformation, maybe I need a bit more board. So you are aware of what a U1 lepton number transformation is. Lepton, let's do it like this. Lepton. So I take a field, for example, the electron field, and I rephase it by a quantity alpha, e to the I alpha, e left. And I can do the same for the neutrinos, e to the I alpha. Now, at a condition, here you have the field psi, or neutrino in this case, and here you have its conjugate. Its conjugate contains the transpose of the dagger, therefore the star. So under a U1 lepton transformation, you will pick up an e to the I alpha here, and another e to the minus I alpha here. So it's not invariant under U1 transformation. And therefore you cannot have, if you want to satisfy this, the Majorana condition, lepton number cannot be a good symmetry, because it cannot be preserved by the Majorana condition. we will see that when we talk about masses at the end of this lecture, indeed Majorana fields arise in presence of Majorana masses, and Majorana masses break lepton number by 2 units. People still talk about neutrinos and antineutrinos in case you're talking about Majorana fields, but it's a bit of a stretching of the nomenclature, if you want. So if you have an ultra-relativistic neutrino, Majorana neutrino with negative helicity will interact as a Dirac neutrino, and therefore you can kind of call it, in quotation marks, a neutrino. A Majorana neutrino of positive helicity will interact as a Dirac antineutrino, and so people commonly call it an antineutrino. But it's a little bit of a stretching of the words. Indeed, technically you cannot talk about neutrinos or antineutrinos if you're talking about a Majorana field. But we usually deal with ultra-relativistic neutrinos, and so this is a kind of a good approximation which makes things clearer. So how are you going to test the nature of neutrinos? That is so important. This is a very strong experimental effort trying to establish the nature of neutrinos. What you need to look at is lepton number breaking, which, by the way, is per se a very, very important issue in particle physics, to understand the physics beyond the standard model. So there are various ways, but the most sensitive one is neutrinoless double beta decay. So a double beta decay is a process in which you start with 2 neutrons and you end up with 2 protons and 2 electrons. Now there is a standard model process which is the 2 neutrino double beta decay, in which one emits 2 antineutrinos. Let me call it this, I call it 2 nu dBd. And this is allowed by the standard model. It's extremely suppressed, as you can imagine, because you pick up a GF squared here, a GF squared here. It's a very, very rare, yes? No, so you need to search for, so the question is about what the experiments are telling us about lepton number. Now, the experiments, what do you mean with experiments? The standard model preserves lepton number. So if you're looking for any process which is dominated, which is driven by standard model, you will not test if lepton number is violated or not. Standard model conserves it, so you will have lepton number conservation in any process in which the standard model interactions are involved, right? In fact, this is a standard model process, and in fact, this conserves lepton number. So you need for other processes, and for instance, this other process is the neutrinoless double beta decay one, which happens when, instead of emitting the neutrino, the antineutrinos, these are exchanged. So you need to look for other processes we have not yet seen, but we can search for. And so this is one of them, the most sensitive one in particular. So this is the neutrinoless double beta decay. We have not seen it yet, so we don't know. If we never see it, under certain conditions, we could possibly establish that neutrinos are Dirac particles. Or otherwise we just put limits on the violation of lepton number. The moment we see this, lepton number is violated. For the time being, we don't know. Okay. So it's an extremely rare process, both of them extremely rare. This has not been seen yet. This has been observed in several nuclei. As it is so rare, you can search for it only in very specific nuclei, because generically the single beta decay will dominate. And then it will become difficult to distinguish two coincident single beta decays from a genuine double beta decay. So what you do, you look at nuclei where the single beta decay is kinematically not allowed because the DOTA particle, the DOTA nucleus, is heavier than the initial one. But in many of these nuclei, the double beta decay is kinematically allowed. And so there is a certain number of nuclei, for example, germanium 76, molybdenum 100, calcium 48, xenon 136, and others that you can study. As you see, they are all very, very heavy. And immediately you can imagine the nuclear part of these decays is very complex. We're not really interested in the nuclear side of things, we're interested in the neutrino part. And in fact, you can split the decay rate in the two components. I can use that. So I can write down the decay rate, actually it's inverse, in terms of a phase space factor, which is known, you can compute it just using normal quantum field theory, and it is normalized over the mass of the electron. And then you have the part which depends on the neutrinos, which is called the effective Majorana parameter. Let me call it m beta beta. In the literature, you will also find MEE or a symbol like this, squared. And the nuclear part, these are called the nuclear matrix elements. That you need to compute using nuclear theory. This effective Majorana mass parameter is very important because it embeds completely all the dependence on the neutrino properties. And is defined as such. M beta beta is a sum over the three masses, M1, UE1 squared plus M2 UE2 squared plus M3 UE3 squared. Now let's try to understand why this structure arises. Now, if you look in that propagator there, and you look at the gamma structure that you have, in the propagator, you will pick up not the p/ term in the numerator, but the m term in the numerator. This makes sense from a physics point of view, because this process happens only if neutrinos are Majorana particles. It violates lepton number by 2 units. Maybe I should stress this further. This is a delta L equal to process. So it can happen only in presence of lepton number violation. But where in the theory do you have lepton number violation? It is the mass of the neutrinos. And so the decay rate needs to depend on the lepton number violating parameter, which is the mass of the neutrinos. If that goes to 0, I restore lepton number conservation, and I need to have the decay rate to go to 0. And this is where these M1, M2, M3 come about. And as I told you, technically you see it by looking at the gamma structure and the terms you pick up in the numerator. The other thing is you are using the Majorana condition in that propagator there. Therefore, you pick up a mixing. Well, first of all, that is a new E, but you need to express the propagators in terms of the massive neutrinos, so nu1, nu2, and nu3, which is why you have the sum over the three massive terms. Now, therefore, you will need to express the flavor neutrino nu E or anti-nu E in terms of the massive components. Therefore, you will have the mixing arising UEI. But at each of these vertex, you will pick up an UEI in one vertex. In the other vertex, you are using the Majorana condition. Therefore, you pick up not the UEI dagger, but the UEI itself. And that's why you get a square here and not a modulus squared. So phases in these terms will be important in this sum and therefore in the decay rate. And this is actually how neutrino double beta decay is, at least in principle, sensitive to CP violation, in particular Majorana CP violation. So what we can do now that we understand the structure of this term is to look at what we know from neutrino properties, and we know quite a bit about the masses and the mixing angles which enter here, predict from there the value of m beta beta, and this will give me a prediction for the decay rate, and then I can go and compare with experimental results, bounds, and sensitivities for the future. Okay, so I can do these predictions generically, and I'll do that in a minute. But before doing that, there are some limiting cases for the masses which are particularly interesting theoretically. The first case I want to discuss, so let's look at m beta beta predictions. And the first case I want to pick up is the case in which I have a normal hierarchical spectrum. Which means I have normal ordering, so M1 smaller than M2 smaller than M3, but in addition to that, I have that the smallest mass is negligible. So it's a limiting case. It's interesting theoretically because in many models in which you try to explain the masses and the flavor structure that you observe, you will end up in one of these limiting spectra that I'm mentioning. So in this case, first of all, as M1 is negligible, if you remember from yesterday's formula, in this case we have that M2 is the square root of delta M squared to 1. So is around 10 millielectron volts. And M3 is the square root of delta M squared 3,1, which is around 50 millielectron volts. Then from the first lecture, you remember the parametrization of the elements of the mixing matrix in terms of the angles that we have measured. So you remember that UE1 cos theta 1, 2, cos theta 1, 3, and UE2 is sine theta 1, 2, cosine theta 1, 3, and then there will be a phase, alpha to 1 over 2. This is the Majorana phase. And UE3, right here, is sine theta 1, 3, and then multiplied by a phase which I take to be e to the minus I delta plus alpha 3, 1 over 2. This is the Dirac phase, this is the Majorana phase. you remember in the parameterization, in that Formula 6 in the notes that I indicated on Monday, we have the 3 by 3 matrix to contain the delta phase multiplied by a phase matrix which is diagonal. Okay, so now we have all the elements, we can plug it in here and look at the values we obtain. So in this case, m beta beta, in the case of a normal hierarchical spectrum, is given by m1 we neglect, m2 is delta m squared to 1, and then I have, let me use the shortcut, sine square of theta 1, 2, cosine square of theta 1, 3. Then I'm going to collect the common phase plus the square root of delta m square 3, 1, sine square of theta 1, 3, and then I have e to the minus 2i delta plus alpha 3, 1 minus alpha 2, 1. I've collected that term between the two and I took it off. So now if I plug in values, this is around 10 millielectron volts multiplied by roughly 0.3. Theta 1, 3 is small, so cos square theta 1, 3 is roughly 1. Now this term here is around 50 millielectron volts, but is multiplied by the small mixing angle, and therefore it will give a small contribution. And at the end, at most, when I sum them up, I can get around 5 millielectron volts. But I don't know these phases. So at most, this can give me 1. At worst, this will give me minus 1. So I will get a partial cancellation here, and I will get something which is around 1 millielectron volt. These are the two extreme values, and then the phase can be anywhere in between, and so I will have any value in between if the phase is this kind of phase here, is not 0 or pi. Of course, there's an I here, and here as well. So I can do the same in the other limiting case. I call that the inverted hierarchical spectrum. Which is the case in which I have inverted ordering, and I can neglect the smallest mass, in this case M3. So I can do the same and find the predictions for the inverted hierarchical spectrum. I neglect M3, M1 and M2 are quasi-degenerate, and I will end up having only these two terms. So I will have roughly the square root of delta m squared 3, 1, and then I have a cos square theta 1, 2, sine cos square theta 1, 3, plus sine square theta 1, 2, cos square theta 1, 2, and the phase alpha 2, 1. And again, I can find the two extreme values. So when alpha 2, 1 is 0, I have the sum. So I will have simply the square root of delta m squared 3, 1. This better be a modulus. Delta m squared 3, 1. Which around, as I said, 50 millielectron volts. And if instead, so this is one case, and the other case is when this phase is pi, then I have a minus sign, so I will get the square root of the modulus of delta m square 3, 1, multiplied by cos square theta 1, 2 minus sine square theta 1, 2, which is the cosine of 2 theta 1, 2. If you remember from yesterday, this angle cannot be maximal. If it were maximal, this could go down to 0. Meaning instead is around 33 degrees. And so at the end I get somewhere around 15 millielectron volts. What I would like you to do as an exercise, to do this a little bit more precisely, starting from the formula, obtaining these expressions and then plugging in numbers to get this result. Yes?
Could there be viable scenarios where this m beta is suppressed?
Yes. So this is true, as I will mention in 1 minute, in the standard 3 neutrino case. If you have a partial hierarchy, then you can have an exact cancellation between the 3 different terms. At that point becomes a theoretical question of understanding why you have such a special situation in which MEE is 0. And so you might want to find if there is a symmetry or whatever reason to obtain that. There's also situations in which I extend this scenario, in which I have, for example, additional light degrees of freedom. In that case, here the sum continues. If I have the light sterile neutrinos that some people asked me about, the ones for which we have hints from LSND, mini-boon, etc., then here I have a plus and the contribution from these other light states. Then it becomes a question of why do they cancel out exactly, etc. There is one very natural theoretical situation in which you get an exact 0, which is when you have a very light seesaw. Maybe I'll comment on that later. In a light seesaw, you have here the additional terms, but effectively what you're doing, you're reconstructing the MEE term in the mass matrix, and that is preserved by SU2 to be 0. So in that case, you have a strongly justified reason why you would not see neutrinoless double beta decay. Okay, so these are the predictions. The fact that you have here 15 millielectron volts and here 5 millielectron volts turns out to be quite important from a phenomenological and experimental point of view, because now if I have a measurement, then I can distinguish between the different spectra. And indeed, neutrinoless double beta decay is now being considered a way to get information on neutrino masses. Of course, under the assumption that this is the main contribution to this process. Yes. So, generically, now if I look at any value of the minimal mass, so I look at all possibilities, what you get is plots of this kind. So you have the predictions for m beta beta. And here you have minimal mass, which is m1 for normal ordering and m3 for inverted ordering. In the case of inverted ordering, first of all, you have those predictions. Still, you can neglect m3. You will have a band here, and this is true till around, let me see, 0.01 or so EV. And then as the masses increase, then you go into the quasi-degenerate spectrum, which has a similar structure like that. The extremes are obtained when you have CP conservation, when your phases are either 0 or pi. And for CP violation, you will be in between here. In the case of the normal ordering, So if you have in the hierarchical spectrum, so at very small masses, you have this prediction. So we said this is 50, let's say this is 15 millielectron volts, and this is 50 millielectron volts. And here we are in the few millielectron volts. As I increase the masses, at some point these will join, because when I can neglect the mass square differences, I cannot distinguish normal from inverted ordering in neutrino-less double beta decay. But I can have also this possibility of a cancellation. If you have some partial hierarchy between the masses. So if the masses are in between, the smallest mass in between 0.001 and 0.01 electron volts, then there is this special situation in which m beta beta could even be 0, which means that the decay rate becomes 0, the lifetime becomes infinite, and you cannot really see the process. So the current experimental situation is here, with Kamlan-Zen. And other experiments. The goal of the next generation is here, so that you can test completely the inverted ordering case and then compare with the information you have from other sources, for instance, from long baseline oscillation experiments. And then we are now start discussing how to go beyond that and at some point reach this millielectron volt region. And you see how you can obtain information on neutrino masses. For instance, if you were to measure neutrino-less double beta decay at this level here, then you would either conclude that it is inverted ordering, or it could be normal ordering, but in a very, very narrow range of masses. Now you have information from other sources, for instance, long baseline neutrino oscillation experiments, which tells you the ordering, and then you know if you are in this situation, or you have this very precise determination of neutrino masses. Of course, it's not as simple, because how do you obtain m beta beta? By measuring the half-life time and knowing the nuclear matrix elements. This turns out to be an extremely complex problem, where you have large uncertainties, and so till we don't have these nuclear matrix elements better under control, it will be difficult to obtain considerations, results of this kind. However, I have to say that we have done in Europe this year a quite thorough process of review of the current situation, and there are some very interesting new developments in the computation of nuclear matrix elements with ab initio calculations. And so it is possible that in the not too far future, so in the matter of a few years, maybe this problem of the nuclear matrix elements will become much less severe in neutrino-less double beta decay, which will be extremely interesting. So just quickly, what is the experimental situation? So first of all, how do you measure neutrino-less double beta decay? How do you search for it? So you have these very heavy nuclei which transition from one to the other, emit 2 electrons, and emit or not 2 antineutrinos. So this could are present if you look at the 2 neutrino double beta decay, but what you want is the neutrino-less double beta decay, the non-standard model process. So in these experiments, what you can measure is the energy of the 2 electrons, and if you look at the spectrum of the electrons, in the 2 neutrino double beta decay you will have a spectrum, because the antineutrinos carry away some energy, and therefore you will end up with the spectrum here. This is my dN over dEE, and this is the sum of the energies of the 2 electrons. Now, in neutrino-less double beta decay, you have no new energy carried away by the antineutrinos because they are not emitted, and therefore you will have a peak here at the end. So this is the way we search for neutrino double beta decay in these processes. It's extremely rare process, which also means that backgrounds are significant. Lots of things can mimic an electron track or a bi-electron track in a detector, gammas, alphas, etc., a variety of things. So you need to have very large masses, because the process is very rare, so you need to have a very large number of nuclei. You need to have very low backgrounds, and this really means that you need to go very deep underground laboratories so that you can reduce all the kind of surface type of backgrounds. You need to purify your materials. So in these experiments, it's not sufficient to use normal materials to build your detector. For example, you need to purify your copper for all your electronic junctions, etc., etc. Just as a curiosity, to shield the detector, one thing that they use is lead, but normal lead is too radioactive for these experiments. So there's lead which has been, and the radioactivity comes from activation of some of the components. So lead which has been underground for a long time is very low in radioactivity. So a lot of this lead comes from Roman ships which has been sank, so are 2,000 years underwater. So they have been shielded properly, so they take it and then they bring it to the Gran Sasso or other labs where they do these experiments, and they use that for shielding. So it's, I mean, it's really remarkable. I went once to see one of these experiments, past experiments, Nemo 3 in Modane. So this is the lab which is in the Fréjus tunnel between France and Italy. And so we went in and it was all covered up. It's quite big, maybe 4 or 5 meters tall. And it was all covered up by plastic, and I didn't understand what was going on. So it turns out that the air is too radioactive because of radon. So they had to purify and pump kind of more pure air inside. And then the walls were also all painted up. I mean, what's going on there? The rock was too radioactive, so they had to try to shield the radioactivity from the rock as well. So they are beautiful experiments. So there are several which have been, maybe I can show you the experiments rather than discuss them on the board. So these are some of the experiments which have happened so far. So this is, the most stringent bounds come from Kamlan-Zen. This is the Kamlan experiment that I mentioned for measuring delta m squared to 1 precisely, and using radioactive reactor antineutrinos. So as you know, reactor neutrinos in Japan have been switched off, unfortunately, because of the tsunami disaster. And therefore now you have very low reactor neutrino backgrounds there. And so what they use, they reused the Kamlan detector, which contains a lot of scintillator, and they have put here xenon 136 in this small balloon and look for this process. Now, Kamlan-Zen is a very big detector, and so they are very, if you compare with some of the others, they have a lot of mass, and in this way they could obtain a very, very stringent bound. Here you see how it works. So this is, for instance, is the xenon. Xenon is a very similar detector using xenon 136 with a smaller mass, therefore a slightly worse bound, but it shows you the kind of experimental challenges you have. So this is the 2 neutrino double beta decay spectrum, this kind of purplish magenta line. That is always a background for neutrino double beta decay. Even if you could reduce all the other environmental backgrounds to 0, you still would end up with this. So you need extremely good energy resolution, which is, for example, a characteristic of germanium detectors. And now, and you have all these bumps and lines, etc. These are all backgrounds. The backgrounds come, for example, from uranium, This is a background which was important because this is a silver, and this actually came into the detector because of the Fukushima disaster. They didn't expect it, but then they understood why it was there, etc. It sits right at the end point, so that's why it's problematic, because it sits where you would expect neutrinoless double beta decay to happen. And so you're looking for, you know, a really tiny little bump in this very complicated plot. And it's very, very challenging, but also very interesting. You have experiments using germanium-76, Gerda, Majorana, which are joining together in an experiment called Legend, which is funded and due to start in a year's time. And then you have a completely different technique, which instead measures the electron energies by looking at very, very tiny changes in temperature when your detector is very close to zero temperature. And this is the Quarry technique. Uses currently tellurium-130, and then for the next generation experiment, which is Cupid, instead we'll use molybdenum. In fact, I have them here. This is Legend. It is due to start in a couple of years' time, here, commissioning and the physics run, and uses germanium-76. You see the mass. This is Legend 200, 177 kilograms of mass, and then its successor will have several modules reaching roughly 1 kiloton. And you see the time of lifetimes these experiments can test, 10 to the 27, 20 to 28 years. This is Cupid, which is the next step after Quarry, but this uses molybdenum to reduce backgrounds. I mean, there's some technicalities, and again, it's due to start, well, in a few years from now, and again, we'll reach this 10 to 27 years. And the next, this is uses xenon 136, but in a high pressure configuration, while by Darwin or Kamlansen, they use it, or Nexo use them in liquid form. And so this is the current situation with this. And this is the global context, so there's no plus, which is being prepared in Canada. We have Darwin. This is a dark matter experiment, but we'll have also sensitivity to neutrino double beta decay, and the studies are ongoing to understand exactly what is the limits and the sensitivity they will be able to obtain. And this is the main US program, which is Nexo, which uses 5 tons of liquid scintillator xenon. And there are other kind of efforts in China, in Japan, etc. So it's very, very, very rich experimental program. That's why I wanted to mention it in quite a detail. And you can expect in the next decade to have lots of new results and possibly an observation. That is what we all hope at some point. So this is concerning neutrinoless double beta decay. And I want now to move on to the other questions, which I will try to mention in not too slowly. Maybe we do 5 minutes of break, and then we move on to the determination of neutrino masses and the CP violation. We should start again. Okay, so we said in terms of neutrino masses, we know the mass square differences, but we don't know the ordering. So we need to determine the ordering. And the mass scale. So how can we do that? Now, for the ordering, you remember that the ordering, which means the sign of delta m square, I mentioned that at the end of last lecture, this sign enters in the enhancement of suppressant oscillations in matter. So experiments which can look at matter effects, so there will be long baseline oscillation experiments, particularly Dune, atmospheric neutrino experiments will be able to tell the sign. In particular, Dune has a sensitivity to 5 sigma in not very long, a couple of years. And then there's another technique looking at the interference between the effects due to delta m square 3.1 and delta m square 2.1. These are reactor neutrinos at an intermediate baseline around 60 kilometers. And this is the Juno detector in China, which is due to start next year. In terms of the overall scale, then we have direct searches in beta decay. We said that neutrinoless double beta decay can give some information. And we should not forget cosmology, although we'll talk about this in the last lecture, because cosmology indeed has become the most sensitive way to measure neutrino masses that we have. So I want to mention briefly direct mass searches because the Catherine experiment, after a very long time of preparation and commissioning, finally has presented their first results. It was very exciting a couple of months ago. So let's talk about beta decay. And what one looks is at the electron spectrum. So if I look at the endpoint of the spectrum, so my n over dE, and this is my endpoint. If neutrinos have no mass, the endpoint will be reached in this manner. Now, if neutrinos have a mass, then the electron energy, so this is the electron energy, cannot reach the endpoint, but will reach the endpoint minus the mass of the neutrino. And the spectrum will be changed in this way, will be deformed right at the endpoint. It is by looking at this very tiny deformation that one establishes a bound or tries to measure the mass of the neutrinos in beta decays. In particular, if we maybe we can write down more precisely the differential decay rate in terms of the electron energy. There will be some constant. Then I have the nuclear matrix elements squared, the momentum of the electron multiplied by the energy of the electron plus the mass of the electron. Then I have the energy of the electron minus E0. And then I have the term which is relevant for neutrino masses, which is the square root of EE minus E0 squared minus MI squared. And then there is a Coulomb term. This is the term which is important, and this is the term which is responsible for this deformation right at the end. And let me show you this. So the experiment which is currently most sensitive is Catherine, which released their data. So you see it uses a tritium and tries to measure very, very precisely the energy of the electrons right at the end of the spectrum, using this gigantic spectrometer. Some of you might have seen those pictures of this spectrometer in Germany when they were trying to move it through a village. And So you see the scale of the experiment, and very interestingly, they have the first results which put a bound on the neutrino mass around 1.1 electron volts. So this corresponds to roughly 30 days of data, and this already improves by a factor of 2 the previous bounds which were being put by Troins and Mainz experiments, well, now nearly 15, 20 years ago. And there are plans, potentially, there's some R&D to understand if we can go beyond the sensitivity of Catherine. Catherine will go down to 0.2 electron volts, covering what is called the quasi-degenerate spectrum. But then, of course, we want to try to go beyond that, and the Project 8 is what is currently now being considered as R&D, and there are some very promising developments in that direction. I don't have time to go into the detail, but it's all very interesting. So I already mentioned how neutrino-less beta decay can potentially give us information on neutrino masses. So instead, what I want to do to finish up covering the measurement of neutrino masses is look at the ordering. Okay, so I don't have a lot of time that I want to spend on this, so I will just mention here on the slides atmospheric neutrinos. So in this case, the effects are quite complicated because you have these matter effects, and as you know, the Earth has a density profile with a core, then a mantle, and then a crust. And so you have these kind of steps in the density, which make the neutrino oscillation more complicated. However, there is a sensitivity to the mass ordering, and in fact we expect that experiments, for instance the Spingu and then Orca, they should be able, and Ino as well in India, they should be able to give us information on the mass ordering at least at some confidence level, probably around 3 sigma or so. The current indications, which are still to be confirmed, are in favor of normal ordering, but at very low significance, so below 2 sigma. And the other technique that I already mentioned briefly is using reactor neutrinos and looking at the interference which comes about between these delta m squared 3.1 and delta m squared 2.1 terms. And so you see, this is the probability for nu E disappearance in reactor neutrinos. Remember, we discussed yesterday, this is the only probability you can really measure for reactor antineutrinos, folded in with flux and cross-section, and you're looking at this tiny difference between normal and inverted ordering. This is something that Juno is trying to achieve, and as I said, Juno will start next year. What they need is an excellent energy resolution, around 3% at the MeV energy. Instead, what I'm going to discuss a little bit more detail is determining the mass ordering in long baseline experiments. So, long baseline experiments are experiments in which you use accelerator neutrino, and the distance between the source, which will be an accelerator complex, and the detector is several hundred kilometers, if not over 1,000 kilometers. Currently, there are 2 experiments, which are T2K and NOVA. The energies that typically you use are around, you remember from yesterday, between GeV-ish and a few GeV, which correspond to distances between 300 kilometers and 800 kilometers, which also means that you can see electron neutrinos, you can distinguish electron neutrinos, mu neutrinos, but it's very difficult to see tau neutrinos. So the channels that these experiments look at are nu mu into nu mu, and nu mu into nu E, and the antineutrinos as well. Nu mu's, because all these experiments, as I discussed yesterday, have mu on neutrino beams produced from pion decays. So, and the probability which is particularly interesting from this perspective is the nu mu into nu E1. Now, this probability is a free neutrino oscillation probability, so you can expect to have CP violating effects there because it's sensitive to the full 3 neutrino mixing matrix, and in meta. So it's rather complex, and there have been several different approximations which has been made. I'm going to give you an approximation which is kind of very transparent in the dependence to the various parameters. So you have 4 cos square 2 theta 2 3, sine square theta 2 3, and then 1 over 1 minus RA squared, and then you have a sine square 1 minus RA delta 3 1 L divided by 4E. Plus, we have the CP violating term, sine 2 theta 1 2, sine 2 theta 2 3, sine theta 1 3, delta 2 1 L divided by 2E, sine of 1 minus RA, delta 3 1 L divided by 4E, and here you have the cosine of delta minus delta 3 1 L divided by 4E. And then additional terms which are subdominant. So here I'm defining array to be the square root of 2 G, F, and E divided by delta 3 1 and delta 3 1 is defined as delta m square 3 1 L divided by 2E. Oh, so without the L, just that. Delta m square 3 1 divided by 2E, and delta 2 1 is defined in the same manner. So this array term is the one which is due to matter effects. So for these experiments, usually you don't reach resonance, so array cannot become 1. However, it can be significant. In nova, for instance, is going to be of the order of 20–30%, and in dune, because the baseline is longer, is even larger than that. And so if delta m squared 3 1 is positive, then this term is positive, and here I have an enhancement of the neutrino oscillation probability in this term here. If delta m squared is negative, instead I have a suppression. And for antineutrinos, the opposite happens. So for neutrinos, delta m squared 3 1 positives means an enhancement of the probability. And delta m squared 3 1 negative implies a suppression. And for antineutrinos is the opposite. And these experiments plan to run in both configurations, neutrinos and antineutrinos. And so you can try to check where you have an enhancement or a suppression. Now, as you see, this formula is very complicated. And here I have this term, which although it is due to theta 1 3, which is the small mixing angle, still dominates compared to the other, because theta 1 3 indeed is not too small. It's around 9 degrees, which is sizable. And so this is a kind of a subdominant effect with respect to the first term, and I'll come to that in a few minutes when we discuss CP violation, because this is the term which is sensitive to the delta phase. So experimentally, let me show you the sensitivities of here, Dune and hyper K. So Dune, which is this experiment which is being under construction in the US, we use a beam sourced at Fermilab with an average energy around 3 GeV, and the detector is in the Homestake in the Sudan mine, which is 1,300 kilometers away, and will use 40 kilotons of liquid argon to detect the neutrinos. And this is their sensitivity that you can see here. This is the square root of the delta chi squared, which tells me the confidence level at which I can determine the mass ordering. And this is as a function of the delta phase, which is due to this subdominant term here. You can see that in any case, Dune will be able to discover the mass ordering. Now, there are other experiments, as I already mentioned, taking into account atmospheric neutrinos, etc. But this is going to be kind of the most controlled way we have to determine the mass ordering. So now let's come to CP violation, because we can use this same formula. Apart from the comments that I made about CP violation in neutrino reservoir beta decay, which in any case is very difficult to achieve experimentally, till we don't have a perfect control on the nuclear matrix elements, the best way we have to determine CP violation in the lepton sector is trying to measure the delta phase in long baseline neutrino oscillation experiments using this same formula. And as I said before, so I look at this, I try to measure the probability for neutrinos and antineutrinos in these long baseline oscillation experiments. And if I have antineutrinos, this delta phase, remember U goes into U star, delta goes to minus delta. And so the two probabilities will be different. Now, the problem which we studied for a long time, and I think we now have under control, is that if when you change from neutrinos to antineutrinos, you change delta to minus delta. But as you have also matter effects, you also change this to the opposite. So now you have two sources of difference in the probabilities, and you have to disentangle the two. Now, there are various ways to do that, taking, for example, into account that CP violating effects become more important at low energies, so trying to have spectra, so different, measuring the probabilities at different energies, etc. So it's something that was studied very carefully in the past, and as I said, I think we have it now under control. And it's a subdominant effect, but it is important, and in fact, future experiments will have very good sensitivity. This is, again, the number of sigmas at which you can establish the CP violation. Here for Dune, so you see that, let's look at the 10-year case. If the value of the delta phase is close to where current indications are, so really nearly maximal around here, then you should expect to see a 5 sigma signature, so a discovery within 10 years, and okay, 7 years already might bring you up above 5 sigma. Of course, this band depends on the different values of the true values of the oscillation parameters and the experimental inputs that you have. And the same is true for T2 hyper K. Again, this will go above 5 sigma if CP is nearly maximally violated in the lepton sector. So this is a very important question from a theoretical perspective, and the next generation of experiments will be able to discover leptonic CP violation if the values are somewhat favorable. We have already indications at the between 2 to 3 sigma level, but as I discussed yesterday, we need further confirmation to that. So this concludes the discussion about neutrino phenomenology. There's only one comment that I want to make, which is this, that I discussed many different experiments which can address different questions, sometimes more than one, and sometimes the same question can be addressed in different ways. For example, the mass ordering through atmospheric neutrinos, reactor neutrinos, neutrinoless double beta decay, etc. So the complementarity between this very broad experimental program is very important. I don't have time really to discuss specific examples, but it's something to keep in mind. And when you combine different experimental results, you can even get information, more fundamental information that you could not get from a single experiment itself. And here, if you're interested, I'm happy to discuss that with you more in detail. Instead, what we're going to do now, we're going to use the remaining time, which is at least 10 minutes, yes? 10 minutes, yes. To start the more formal part of the discussion about neutrino masses. So, we know that we have neutrino masses. We know that we are going to try to measure them more precisely and get more information in the coming future. Now, how does this impact on our theoretical understanding of the extension of the standard model and the physics beyond the standard model? So the first thing we need to do is to understand how we can write down a neutrino mass extending the standard model Lagrangian. So let's discuss neutrino masses. So what kind of masses can neutrino have? Well, the simplest case is the Dirac case, like all the other fermions. So a Dirac mass term will be written as a mass, and then we will have the neutrino field left bar, nu right, plus the Hermitian conjugate. So I need two Weyl fields, a nu left and a nu right one. So just as a comment now, and we'll go into more detail about that tomorrow, in the standard model you don't introduce right-handed neutrinos because we have not seen them. So this is already kind of a departure from the standard model because we are introducing right-handed fields. An interesting property of this mass is that it conserves lepton number. In fact, under a U1 transformation, I can transform nu left and nu right in the same manner, u alpha nu left and e to the I alpha nu right, which means I'm giving the same lepton number to nu left and nu right. This is under a U1 lepton. And you see here that the mass term remains invariant. Nu left bar contains nu left dagger, and so picks up the opposite phase, and therefore it cancels out. Now, generically, this M nu is a matrix. So to find the masses, I need to diagonalize M nu, and the neutrino masses will be the eigenvalues of this matrix. So, to do that, I need to use a biunitary transformation. in which I use two unitary matrices, V, and this will be the diagonal matrix that contains the values of the masses, U dagger. And now, this term here diagonalizes, can be reabsorbed in a definition of the left-handed field. So my massive fields for the neutrinos and left will be V nu left. So these are the flavor fields, and these are the massive fields. And therefore, this will enter into the charge current Lagrangian, and from there into neutrino oscillations. As I will explain somewhat briefly tomorrow, in reality you have also contribution from the diagonalization of the charge lepton mass matrix. And so if I can have a special structure for the charge lepton and the neutrino mass matrices, this will induce special values for the mixing matrix, and therefore can explain the values of the mixing angles we observe. So this is kind of the basic idea behind trying to explain the fact that theta 2,3, for instance, is quite close to 45 degrees. Okay, so this is the same as for all the other charged fermions. Now, we can have a different type of mass for neutrinos, which is a Majorana mass term. And this is specific to neutrinos because they are the only neutral fermions in the standard model. For this, you don't need two different Weyl fermions, just need one. You still need a right-handed field, but you remember that we discussed earlier and said that it was important. I can use as right-handed field the charge conjugate of the left-handed nu left, which is right-handed, as we discussed earlier. And so in this case, I can write down a Majorana mass term as a Majorana mass, and then I can use nu left C, which is right-handed, bar nu left plus Hermitian conjugate. There's another way, which makes some of its properties more transparent, to write this. This is also equal to nu left transpose C dagger nu left. And I would like you to do this as an exercise. So express nu left C in terms of its definition, C nu left bar transpose, and come to this expression here. And from here you see immediately that this term breaks its lepton number by 2 units. In fact, if I do a U1 transformation, so this will go into e to the alpha nu left, and this matrix, this mass term here, nu left t nu left, will go into e to the 2I alpha nu left transpose nu left. So Majorana mass terms break lepton number, which also means they will induce Majorana neutrinos, as I will show you right now. A property which is interesting for these mass matrix, it is symmetric. So is symmetric. You can show that. Is equal to transpose. This is an important property because it will then determine how I diagonalize this. And again, I leave it to you as an exercise to carry out. And because it is symmetric, now I just need one matrix to diagonalize it. So again, I need to diagonalize this mass matrix to find the values of the masses. And so I will have that mm is equal to U dagger transpose M diagonal U dagger. So I just need one mixing matrix. And then again, I can write down N left as U new left. These are the massive fields, these are the flavor fields, and then from there U enters into the charge current Lagrangian, and from there into neutrino oscillations, and I can try to match observations with theoretical prediction. Sorry, this is a dagger. Oh, it's interesting that I can rewrite that mass term in the Lagrangian in the following way. So, my Lagrangian can be rewritten as minus 1/2 chi bar, the diagonal term, chi, where chi is defined in terms of the massive fields as n left plus n left c. But this, what type of field is this? It's a Majorana field, right? So, we have shown that I can start with a Majorana mass term, and this will induce Majorana fields. So I will take 2 more minutes, because then I conclude this discussion about the type of neutrino masses, which is the case in which I have a Dirac plus Majorana mass term. So, if I now have the two Weyl fermions, new left and new right, I can have both a Dirac mass term and a Majorana mass term for the left and one for the right fields. So, my full Lagrangian will contain the terms minus m new left bar, new right, actually I define it as new right, new left here, minus 1/2 new left t m c dagger new left, actually this is a plus 1/2 new right t m right, I call this left, c dagger and right, plus the Hermitian conjugate of this. So this is my full Lagrangian. Now I need to find the the massive states of this Lagrangian, and so the first step that I do is rewrite it in the following form: 1/2 psi minus 1/2 psi c left bar with a big matrix M, psi left plus Hermitian conjugate, where I have defined psi left to be a combination of new left and new right C. And this big matrix M contains the Majorana mass term left and the Majorana mass term right on the diagonal, and the Dirac terms on the off diagonal. It's a nice exercise to show this, actually, so I suggest that you do that. But now I have something which is exactly in the same form as before. Therefore, I can do exactly what I did before. I can diagonalize this mass matrix M. I can find the mass states. And then from the mass states, I can define the chi field, which will be a combination of new left and new right C, and will be a Majorana field. So I do exactly the same steps as before, but the end result of that will be that chi is a Majorana field. And this makes sense if you think of it physically, because you have broken lepton number by these Majorana mass terms. And therefore, lepton number is not a symmetry anymore of your theory. Therefore, your expectation should be that the fields, the massive states, are Majorana fields. Your massive fields are Majorana. So, now, with these ingredients, what we do tomorrow is to look how to generate these terms in a consistent theoretical framework. Now, I cannot write down simply these terms here because these terms break SU2, the SU2 gauge symmetry. Therefore, I need to find an extension of the standard model which will induce these terms once I break SU2, and then we'll discuss then Dirac masses, but most of the time will be spent on Majorana masses, the seesaw mechanisms, and their consequences. Okay, thank you.